So far, we have discussed approximation algorithms in general. Now, we are going to study a specific problem, the vertex cover problem. First, I need to give you the definition of the vertex cover problem. Here is a vertex cover. Look at this blanket. The vertices on that blanket touch all the edges of the graph that appears at the bottom of this screen. So, the vertices under the blanket, 3 of them, are a vertex cover for that graph. And by the way, the character represented here is Linus, a Charlie Brown character. I like to give definitions from examples, so let us start with a famous example of a graph that is often used to prove counterexamples to show that certain conjectures do not hold. On this graph, how will you construct a vertex cover? We have to pick a certain set of vertices. Let me start. Let's say I will take the top vertex, vertex A. A covers 3 edges of the graph. I drew them in red. 3 edges, so far so good. But there are still edges uncovered, not yet covered on this graph. So I have to keep going. So I will pick another vertex on this graph. For example, I can pick a vertex at the bottom left of my figure. B. B covers 3 edges. Good. Now I need to continue. Pick more vertices to cover all the edges. Another one. C. C covers 3 edges, but one of them is already covered by vertex B. No matter. It does not matter that an edge is covered by both endpoints. C covers 2 more edges. I keep going. Let me pick vertex D, then vertex E, F, and voila! This, my set of 6 vertices, A, B, C, D, E, F, that is a vertex cover of the graph. Every edge in this graph is covered by at least one of these vertices. Edge BC is covered twice, but all in all, every edge has at least one endpoint in the cover. So that's a vertex cover of size 6. If every vertex has weight 1, then the weight of my cover is 1 plus 1 plus 1 plus 1 plus 1 plus 1, 6. This is optimal. It is not possible to cover all the edges of this graph with 5 vertices. Why is that? It's easy. Easy to find an argument to prove that 5 is not possible. Indeed, observe the outer part of the graph. It's a cycle of length 5. Well, if you want to cover all the edges of a 5 cycle, you need at least 3 vertices. Now observe the inner part of the graph. It's a star. A star with 5 points. Well, a star is just another way to draw a 5 cycle. So we also need 3 vertices inside the graph to cover the inner cycle of a graph. All in all, we need at least 6 vertices, so the solution I gave you, A, B, C, D, E, F, is optimal. It minimizes the weight of the vertices that got chosen. So that's the vertex cover problem. Given as an input, a graph, where every vertex in the graph has a weight, we have constructed as an output a subset of the graph vertices that covers every single edge of the graph and whose total weight is minimum. The sum of the vertex weights is minimum. This is one of the most fundamental problems of combinatorial optimization. So, I have given you a definition of the vertex cover problem. Now, I will give you another formulation, more algebraic, as an integer program.